Okay, so I think we're already familiar with the ether functional group. Ethers can be considered to be another organic derivative of water, the other organic derivative of water being alcohols. Only, of course, these two groups, R1 and R2, neither of them can be a hydrogen for obvious reasons. If either of these is a hydrogen, you don't have an ether, you've got an alcohol. So, so other than that, this is it's quite general. R1 and R2 can be pretty much anything you like. Ethers can be cyclic. You're already familiar with, for instance, THF, tetrahydrofuran. That's a cyclic ether. Other common ethers that we use, probably the one you'll run into the most is diethyl ether. You can actually also call it ethyl ether, though that always bothered me. And even in fact, you will sometimes hear people just say ether, and we mean this when we just say ether, because it's the most commonly used ether, very, very commonly used as an industrial solvent. Other commonly used ethers as industrial solvents would include methyl tert-butyl ether, or tert-butyl methyl ether. Actually, I think that would be a little bit better because the T in tert doesn't count and the B in butyl comes before the M in methyl, but I don't think anyone will put you under arrest if you call it methyl tert-butyl ether. We used to also call this MTBE for short. And MTBE was also a gasoline additive until at least I think maybe sometime in the 90s, round and about there, maybe around 2000. But methyl tert-butyl ether is not the greatest on the environment, so they stopped using that and started using ethanol as a gasoline additive instead, which is much more benign in the environment. I'm just trying to think of other commonly used ethers that you'll see used as solvents. You might run into 1,4-dioxane. That's another pretty commonly used one. I feel like I'm missing one. Oh, 1,2-dimethoxyethane is another one. I think I've even seen this called DME for dimethoxyethane, or you could also call this, if you really wanted to, ethylene glycol dimethyl ether. And ethylene glycol is HOCH2CH2OH. And that also gives you some ideas about how ethers are named. I think you'll find naming ethers to be pretty straightforward. You can name an alcohol, you can name an ether. And if you can name an alkyl halide, you can name an alcohol. And if you can name an alkane, you can name an alkyl halide. So that's why I always say, once you learn how to name alkanes, that's probably 90%, if not more, of what you'll need to know in order to name anything with any functional group. So these are the most commonly used ones, at least in terms of solvents. I also want to remind you about epoxides. So epoxides we make from alkenes. This is a reaction we know already using some peroxycarboxylic acid. This could be MCPBA, this could be peracetic acid. Doesn't really matter, but you'll get an epoxide. Forgot a bond, an epoxide. And I think this was an 8-7. Let me just double check that for you. I think I put it in your class notes. Yep. So that's where you'll find it if you need to review that. Also good review for the final exam. So epoxides are special, as I think we've pointed out. They do still fall under the category of ethers. They fulfill the definition, but epoxides are very much more reactive than standard ethers like all of these. Any other kind of ether is going to be pretty unreactive. And again, that's why we like using them as solvents so much, because one of the things we kind of expect of a solvent is that it will not react with anything in the reaction mixture, or at least react very much more slowly than our organic starting material that we want to react. Epoxides are different, as you can imagine, because of the strain, the tremendous ring strain in this three-membered ring, or angle strain, you can also call it. Epoxides are much more susceptible to nucleophilic attack than other ethers are. And so we'll get to that, I think, on Monday. That's going to be one of our major topics on Monday. So epoxides are special. They're much more reactive. The remaining ethers, not so much. It's pretty hard to get an ether to do anything. And like I said, my goal by the end of class today is to show you just how far you have to go in order to get an ether to react. Good, so I think that's all I need to say about that. Your book, like every other book I've encountered up till now, talks about crown ethers. And I used to spend quite a bit of time on it, and I realized over the years, that's silly of me. I always feel guilty spending a lot of time on these things, but I'll mention them since your book does. Drawing the structure of a typical crown ether is kind of fun. I could have done that a bit better in the bottom there. So that's an example of a crown ether. They are macrocyclic polyethers. Macrocyclic meaning big ring polyethers. And this one, if you count it up, you'll see that along with the 4 oxygens, you've got a 12-membered ring. So this one we call 12 crown 4. It's pretty easy to name crown ethers. And we also have 15 crown 5 and 18 crown 6. And you can probably guess at the structures of those pretty easily. They correspond really well to the structure of 12 crown 4. And like I said, I don't want to spend a lot of time on this. These are used to some degree as phase transfer catalysts, which I think you'll have heard of in the lab program. They seem pretty obsessed with phase transfer catalysis in our organic lab program, which is fine, I suppose. These are also used to dissolve alkali metal salts in solvents that they otherwise wouldn't normally dissolve very well in at all. And the reason is, to start with 12 crown 5, 12 crown 5 just happens to have exactly the right size cavity in the center of the molecule to catch a lithium cation, like this. And so if you add a lithium salt, then this thing is going to catch the lithium cations, at least to the extent that you put 12 crown 4 into the mixture. And now your anion is all the more reactive. It's essentially a naked anion. And so you can get things to work, you can get things using lithium salts to work in rather nonpolar solvents that otherwise lithium salts don't dissolve in. And yes, as you would then guess, in 15 crown 5, you've got a cavity that's just the right size to grab a sodium ion. And in 18 crown 6, you've got a cavity that's just the right size to grab a potassium ion. Now, as to whether someone's made 21 crown 7, you know they have. You know someone's done it. I haven't looked into it, but I don't think I have to. I'm that confident it's been done. There's no way that I'm the first person to think of it. And as to whether that's got a cavity in it that's just the right size to grab an ion of the next alkali metal, I can never remember whether that's rubidium or cesium. I think it might be rubidium is the next one. Again, that's got to be known at this point, but we hardly ever use rubidium or cesium salts, so it's kind of a moot point. Lithium, sodium, and potassium are much more commonly used. But I really almost feel bad even spending that much time on crown ethers, since I don't think there's something we're ever going to use in the future. In organic too. So I'll mention them since the book mentions them. I want you at least to be able to read that and understand what they're talking about. But I don't think these things are going to be of any consequence to us in the future. So other than that, I think with that, we're ready to get into how to make ethers. And we'll do the bad old way first, and then the newer, gooder way we'll do second. Any questions so far on just sort of structure and properties? So, I forgot to say some properties. Certainly, I think it's fair to put pretty much any ether, especially these ones we use as solvents, to put them in the category of polar aprotic solvents. I think that's reasonable to do. Since ethers are pretty polar, there are certainly things that are more polar than ethers, but I think it's reasonable to consider THF and diethyl ether to be polar aprotic solvents. I'm comfortable with that. In terms of preparation of ethers, the old way involved essentially condensing two alcohol molecules. And all you would need all you would need for that, besides the alcohol, is an acid catalyst, and then maybe heating it. This method is pretty limited, though, because since it goes by an SN2 reaction, as we're about to see, it only works if the alcohol is primary. So this is to be a primary alcohol. And basically, if you wanted to think of it as a balanced equation, it's two alcohol molecules in the presence of some acid catalyst, making the symmetrical ether that you see here. And of course, you'd also get a molecule of water out of it. But this is a very limited reaction. You can only make symmetrical ethers, and you can only use primary alcohol since it goes by an SN2 mechanism. Did I say E2 before? I meant SN2. And I think we can understand clearly how this would work. Let's say that we took one butanol and we added a bit of an acid catalyst, maybe a little bit of sulfuric acid. Well, that's going to protonate some of the alcohol molecules. So in addition to our alcohol, you'll also get some of its conjugate acid. That's going to come just automatically by protonation once you put the acid in. So what you see written here is what you should write down. That's a perfectly valid way of showing it. You just get this automatically once you've added a little bit of sulfuric acid or something. And completely unsurprisingly, this is just going to undergo an SN2 reaction. You've got a primary substrate with a good leaving group. And so that's going to give an intermediate that looks now like this. And of course, now all we need to do is pull that proton off and we're done. Well, I don't see anything that can really do that for us except for another molecule of the alcohol, which we've got in plenty. Whoops. We've got a veritable ocean of this alcohol around. And so that will pull off that proton and we'll get dibutyl ether. And for all I know, that's actually how they make dibutyl ether in the chemical plant and chemical industries. Couple comments on this. You might wonder why we can't use a water molecule to pull off that proton. The reason is, although we do get 1 mole equivalent of water, that water is drowning in an ocean of 1 butanol. And so I don't think it's reasonable to use that since the water is so outnumbered by the 1 butanol. By definition of this being the solvent and our main reactant. So that's why I think that's the most reasonable way to show this reaction. But this is nothing other than an SN2 reaction. No mystery there in terms of the mechanism. So this does work, but it's very limited. You can only make symmetrical ethers, and you can only use primary alcohols. So if you want to make a symmetrical ether of a primary alcohol, this is your method. Anything else, you need something more general. And so that will get us onto the Williamson ether synthesis method, which is going to be there's going to be like maybe about two more main topics today. We're going to end in a little exercise that had been a reef thing. It was still only going to be attendance today. So I'll try my best to come up with an actual reef polling session for our last class on Monday. But be that as it may, please do register your attendance. But I realized in the previous class when I put up the PowerPoint, something went wrong with it, and so certain really important parts of molecules got cut off. So I don't know what happened. I'm going to have to remake that and re-upload that since that wrong version is already on eCampus. I'm going to try to get that done today. So I'll just write it out for you instead. I'll try to end, with like maybe 5 minutes left or something like that. Good. So, and again, all of this is going on YouTube. So remember, whenever there's something you need to write down, you can always just pause it. That being said, any questions so far? Chat is certainly quiet. I assume you guys can hear me. It's Friday, I understand. Good, so let's talk then about the Williamson ether synthesis. We need a way to make ethers that's more general than, that, because we have to be able to make ethers that are asymmetrical and using other than primary alcohols. So the idea is, in the Williamson ether synthesis, this is also going to be nothing other than a glorified SN2 reaction. And what we'll do is we'll start with an alcohol. And I'm going to be very generic here at first. I'm just going to say minus H plus. We're going to treat this with some reagent that will deprotonate the alcohol, or one way or another, give us the corresponding alkoxide ion, the conjugate base of that alcohol. So this could be a strong base, and I'll go over some examples of strong bases, ones that we're already familiar with, in fact, that will do that for us. And there's one other process that I want to make you aware of that doesn't actually use a base. Instead, we're going to take the proton off through a redox reaction. We're going to reduce the H plus in the alcohol to hydrogen gas, and in so doing, get our alkoxide ion. Once we've done that, our second step is going to involve some alkyl halide, preferably primary. Secondary is fine too. The yield might be kind of low. Tertiary is right out, because we're going to do an SN2 reaction. And as such, we'll get an ether of this type. Whoa, that's R2 over there. Plus various inorganic side products, that depending on what we use to pull off the proton and so forth, depending on what the halide is, or maybe that's a tosylate. So depending on all those, we'll get other inorganic side products. But certainly our major organic product, the one we're the most concerned with, is this ether. And apart from that, you don't want your alkyl halide or alkyl tosylate to be, we'll say that it can be primary or secondary, maybe secondary, but not tertiary. That's not going to work at all, because you can't do an SN2 reaction on a tertiary halide, as we already know from chapter 11. So before we get into specific examples, I told my previous class also, when I was driving in this morning, I was thinking about this, and I realized this is something that I think has tripped up students in the past. So I want to make sure I'm really, really, really clear about this process of pulling off the proton, and what are the species that you'll need to know that can do it, even though they're species you already know, and just make sure that I'm really clear on that, how to get from the alcohol to its conjugate base. And we're going to need, of course, a base that's strong enough to do that. Now, for most alcohols, with a possible notable exception being phenol, but for nearly all alcohols, hydroxide is not going to be a strong enough base to do that, because water and alcohols are at best comparable in acidity. So we need something stronger than that. One base that we know already that can do that for us, I'll just be very generic here with R1OH. One base that we know of that can do that for us is sodium amide in liquid ammonia. That's the conjugate base of ammonia, or sodium amide is. And remember, whenever you see NH2, NaNH2, remember that NaNH2 is this. It is this anion, right? The sodium ion is just a counter ion. That's a spectator ion. Doesn't play any role in the chemistry. But NH2 minus is a more than strong enough base to pull the proton off of an alcohol. No wonder, because the pKa of ammonia is somewhere in the 30s, and the pKa of alcohols is not even 20. So no wonder the conjugate base of ammonia is a strong enough base to do that. And that will give you the alkoxide. And if you want to think of that as R1O minus Na plus, that's fine, just as long as we're clear that there's not a covalent bond between sodium and oxygen. And I should also mention, sometimes you will just be flat out given the alkoxide ion. I think OWL sometimes does that. They're implying that the first step has already happened, and so they'll just give you the alkoxide. And that's reasonable, because there's, I would say, any and all of your simple alkoxides, methoxide, ethoxide, isopropoxide, tert-butoxide, things like this, you can buy those as, or again, when I say you, I don't know if you can buy them. I'm not so sure even I could buy them so easily. But they're available, since I don't have a research group, but they're available at chemical companies as normally as solutions in the corresponding alcohol, in the conjugate acid. So NH2 minus is one base that will do that for us. Another base that I think that will do that for us is the hydride ion. You're familiar with species like sodium hydride or potassium hydride, and you can use these in an alkane solvent or maybe in diethyl ether. That would be fine also. That's not going to react with sodium hydride. Remember, the hydride ion is the conjugate base of H2. So that's a really strong base. And H minus is more than strong enough to pull that proton off for us and give us the alkoxide ion also. What about other bases that we know about that can do this for us? Well, what about organometallic reagents like alkylithiums and Grignard reagents? Those are certainly very strong bases as well. They're the conjugate bases of hydrocarbons. So if we treat our alcohol with, let's say, butyl lithium, you'll also see this as BuLi. Well, the butyl lithium is going to act as a carbanion. The electrons in the carbon lithium bond are going to swing away from the lithium and make Li plus and pick up the proton and give you your alkoxide. The other product will then be butane, just like the other product over here will be hydrogen gas, both of which are gases and will just bubble out of the mixture. But that will also quantitatively give you the alkoxide ion. And then there's another method that you'll be exposed to, which doesn't involve an organic mechanism. It's an inorganic process. It's a redox reaction. And that is that you can take an alcohol and react it with some alkali metal. And again, here I mean the element sodium. So sodium metal, oxidation number 0. And you can also use lithium or potassium. Those are also fine, any alkali metal. And in the end, you will get the alkoxide ion. Of course, if you want to be mass balanced, you'll get a sodium ion, and you will also get half a mole of hydrogen gas. That looks dreadful. Let me write that again. So now the equation is balanced. This is a redox reaction, so there's no mechanism. There's no way to show that with curved arrows, since it's a redox process. What's happening is the alkali metal is getting, let me see now, oxidized from 0 to +1, and the hydrogen in the alcohol is getting reduced from +1 to 0. Right now that's elemental hydrogen, so the oxidation number is 0. And sure, if you were so inclined, if you don't like fractional coefficients and you want to multiply it all through by 2, fine. I have no problem with that. I also have no problem with fractional coefficients. At least occasional simple fractions. Not 49 over 117 or weird things in front of every single species maybe. That'd be a little much. But occasional simple fractions, 1/2, 3/2, I see nothing wrong with that. Most Gen Chem books are kind of against that, but I have no problem with that. But you can think about it either way. So again, there's no mechanism for this. There's no way to show that with curved arrows. It's a redox process. But that's another way that you can make the alkoxide ion from an alcohol, is by adding some of an alkali metal. Sodium's probably the most commonly used, but lithium or potassium would also work. And the only thing it's going to affect is what the counter ion is going to be. So all of these are ways of deprotonating that alcohol. Unless, as I said, you're given the alkoxide outright. Sometimes you might be. Owl might do that to you sometimes. Heck, even I might do that if I feel like it. But if you do need to make the alkoxide, these are examples of bases that will do that for you. Sodium amide, sodium or potassium hydride, any alkyl lithium or Grignard reagent, or you can also use this redox method. So I just wanted to go through that very step by step and very, very, very slowly and clearly, just to make sure that everyone's okay with deprotonating alcohols. Any questions on any of that before we get to some examples, actual examples of Williamson ether synthesis processes? Well, then let's do an example or three. Let's suppose that we took isopropyl alcohol and we treated this first with sodium hydride. So mechanism is fairly obvious. Actually, although the mechanism is obvious, let me write it out. Maybe in diethyl ether, or you could do it in pentane or hexane. That would be fine also. So the hydride ion would pull that proton off for us, and we'll get H2 gas, which will bubble out of the solution. Please do not light a match, and you'll get the isopropoxide ion. And then we just need to treat this with some alkyl halide or tosylate, preferably primary. Let's suppose that we used allyl bromide. Actually, did I hear correctly that you guys have used allyl bromide in organic lab here? Or maybe it happens next term. Nasty stuff. Oh, you have used it. Nasty stuff. Very powerful lacrimator, meaning it'll make you cry. So, and not in a good way, but also very reactive to SN2 reactions. And that's all that's going to happen here. This is why for best results, you want your alkyl halide or tosylate to be primary. And you will get allyl isopropyl ether. At least that's what I think we should call that. I think that's a little better because A comes before P. And if I recall correctly, the I in iso doesn't count. There's so many rules. But pretty easy because A is at the beginning of the alphabet, so we know that's got to come first. Good. So that's just one example. Let's do a few more. Let's say we started with cyclohexanol, and let's say we treated this first with, well, let's in fact use the sodium metal, and maybe diethyl ether is the solvent. Well, again, there's no mechanism to show that you can use to show that. That will just give us the cyclohexyloxide. For the product, well, we've covered that already. When you do and do not have to show electrons. Here I didn't, so I think you can draw your own conclusion. Good, so you'll get the cyclohexyloxide ion, and now we treat that with, I don't know, what do you like? Benzyl bromide. I do use that one a lot. So for questions like that, if you do or do not need to show something, you can take your hint on that by what I do. Basically, if I show something, it probably needs to be shown or is a good idea to show it, and otherwise not. Not necessarily anyway. You can also get some hints in that by looking at exam answer keys, by the way. Anyway, this is now going to undergo an SN2 reaction. I should have pointed out, this is an SN2 step. This also is going to be an SN2 step, right? There's nothing weird about this reaction for us. We're familiar with SN2 reactions by now. Basically, I think I could also say this. Basically, I think it's important to put lone pairs when we're trying to communicate something with them. I didn't put them here on this structure because I wasn't doing anything with them. Here I'm showing a mechanism, so I'd better put them. Here I'm just drawing a structure, so we don't really need them. So that's usually my rule of thumb in terms of whether I show electron pairs or not. Good, so you would get that product. And I guess sodium bromide also. Now, you can also use this to make phenyl ethers. You could start with phenol. Now, phenol, as you'll recall, is very much more acidic than aliphatic alcohols like cyclohexanol and isopropanol. So you don't need to go as far as dissolving metal or hydride or NH2- or like that. Here you could get away with using sodium hydroxide in water. That's now a more than strong enough base to pull off the proton. Now, if you put NaNH2, NH2 liquid, or if you put butyl lithium or NaH or something, it's fine, it would get credit. But I do expect you guys also to know that here you can get away with a weaker base. And the hydroxide ion is now more than strong enough in terms of basicity to pull that proton off for us. Remember that phenol is anywhere from 1 million to 100 billion times more acidic. Is there supposed to be an H? No, I was just using sodium metal. You could do that with NaH. If you put NaH, it'd be correct. That would have a mechanism, though. So if it said to show the mechanism, you'd need to show the mechanism. But you can certainly do that with dissolving sodium metal. So when this goes onto YouTube, look about, I don't know, 10 minutes ago, maybe 5 to 10 minutes ago, and we discussed that. And we showed there what you had to put down for it. But certainly you could use sodium hydride if you wanted to. You could use butyl lithium, that'd be fine also. Or a Grignard reagent, that'd be fine also. Anyway, sodium hydroxide is going to be a more than strong enough base to pull the proton off of phenol for us. And again, if you put a stronger base, it's fine. It's not wrong. It's acceptable. But I do expect you guys also to know that you can get away with a weaker base like hydroxide here. Good. Oh, minus charge. And now we'll treat this with, let us say, 1 iota butane, pentane. 1, 2, 3, 4, 5. Well, again, you're going to get an SN2 reaction. And you'll get, what do we want to call this one? Pentyl phenyl ether or something like that. That's my story, and I'm sticking to it. Good, so these are examples of the Williamson ether synthesis in action. On Monday, we'll also learn that you don't even have to use an alcohol. You can even use a thiol, SH, instead of OH. And that way you can make a sulfide instead of an ether. And in fact, remember, thiols are also much more acidic than alcohols. We talked about that a couple chapters ago. So again, sodium hydroxide is more than a strong enough base to deprotonate a thiol. And another thing you might encounter is, again, sometimes you might just be given the alkoxide straight up and then go ahead and react that with some alkyl halide, preferably primary, and you can get the ether in this way. So again, the Williamson ether synthesis is quite general. The only thing is you don't want your halide or tosylate to be tertiary. That's a no-go, because we can't do an SN2 reaction on a tertiary halide. So preferably methyl or primary. Secondary might be okay also. Might get a somewhat low yield, but it should at least work to some extent. Good, I think that, what are we at in terms of time? I think that's all I really need to say about that. And I refreshed your memory, I think, on how to make epoxides, right? We use peroxyacids on alkenes, and again, a reaction that's quite general. So with that, in our remaining 15 or so minutes, I want to cover the topic of like I said, just how hard you have to kick an ether, other than an epoxide, which we'll get to next time, before it will actually react. Any questions before we do that? Yes. Well, the alcohol doesn't have to be primary. The question, by the way, is what you need to show when you're asked to draw Williamson ether synthesis. So this alcohol can be anything, secondary, primary, or tertiary. Is that? Right, yeah. You'll start with, again, this can be any alcohol, even a phenol, and in fact, this can even be a thiol. That can be SH instead of OH. And I think you would know what to put based on, I don't think you're going to get asked to draw a Williamson ether synthesis. There would be some idea of what product you're aiming for at least. But yeah, as long as you've got an alcohol of some kind, I think I see what you mean now. There are questions in OWL like that. Here's an ether, how would you make it? And there's sometimes more than one right answer, sometimes not. If one of the residues is tertiary, then you'd better make that your alcohol, not your alkyl halide, because you're not going to get an SN2 reaction in a tertiary alkyl halide. Other than that, the sky's the limit. Yep. Good. Well, I think enough about that then. Good. So, as I've said, there are very few reactions that ethers will undergo. One of those very few reactions is, you could call this maybe acid cleavage of ethers. And the general idea here is we're going to take our ether and treat it with an excess of some hydrogen halide, HCl, HBr, or HI, and nothing else, by the way. So this shows you just how far you have to go. Those conditions are just about as nasty as you can hope for. I'm not even talking about HCl, HBr, HI dissolved in water. I'm talking getting out your gas canister and bloody well putting in pure HCl, HBr, or HI. That's really nasty. And in general, you can expect to get both alkyl halides. And of course, you'll also get a molecule of water out of it. The fate of the oxygen in the ether is that it will wind up in a molecule of water. And that reaction is actually mass balanced. So we'll go over the mechanism in a second. Actually, you already know all you need to know in order to come up with the mechanism. So I'm going to give you an exercise where you come up with that yourself in just a moment. We'll end class with that. But otherwise, basically, you look at what are the two residues that you have attached to the oxygen, and you turn them both into alkyl halides using whatever halogen you're given. So that's all there is to that. There are notable exceptions to this. We do require that R1 and R2 not be either aromatic or vinylic. And these are terms we've defined already. In cases like this, you don't get the alkyl halide on that side. And I'll show you examples of both so you can see what I mean. And the reason is the carbon-oxygen bond is too strong on those. So you don't get cleavage of that carbon-oxygen bond. So in an ordinary case, let's say we had cyclopentyl ether, just because it's fun to say. Or is it pentyl cyclopentyl ether? Who knows? Who cares? And let's say that we treated this with an excess of HI, hydriodic acid. I would expect that the two organic products you'd get would be iodocyclopentane and 1-iodopentane. And of course, you'd get water also. Read the directions in OWL in case they may well want you to make another sketcher box and put H2O in it. You know, but these are the only organic products that we're concerned about. Or to do another example, let's say that we had tert-butyl, I'm feeling uncreative. I'm not feeling very creative. Let's say we had methyl tert-butyl ether. And let's say we treated that with excess HBr. Well, I would expect we'd get tert-butyl bromide and bromomethane and water. So you just pop off the two alkyl residues from the ether oxygen and stick halogens on them. The mechanism, by the way, is going to be SN1 or SN2, depending on the structure of the alkyl residue. But both of those are going to be possible. And like I said, that's going to be sort of It was supposed to be our reef exercise today, but the thing got messed up. So let's look at an example of an aromatic ether. Let's say that we had phenyl-butyl ether. Enough CH2s, let's phenyl-propyl ether. And let's say that we treated this with an excess of HCl. Well, you're not going to get chlorobenzene. You'll just get phenol because, again, this carbon-oxygen bond is too strong. So you're not going to cleave that bond. You will, though, get 1-chloropropane. And of course, you won't get water because the OH is still stuck on the benzene ring. So again, that bond is too strong to the aromatic ring. What if you had a vinylic ether? Someone showed me an example kind of like this the other day. And if we treated this with, let's say, an excess of hydriodic acid, well, you'll at first get that vinylic alcohol. You will certainly also get 1-iota-butane. That's all there is to it, right? Yeah, 4 carbons. So you will get those at first. You can't cleave that carbon-oxygen bond because it's too strong. And there's also another reason that you're not going to get to cleave that bond. You wouldn't even have a chance even if you wanted to. A couple chapters ago, I think in chapter 9, we defined enols as being something like this. And we said that they tautomerize. You're not responsible for the mechanism yet. We'll learn it next term. But I gave you a 3-step method to go from the enol to the corresponding keto form. One is you'll turn your carbon-carbon double bond into a carbon-carbon single bond. You'll also turn C single bond OH to C double bond O, and then you'll find another carbon out here that lacks an octet, so you'll stick a hydrogen on it. And essentially what you'll get in this particular case is acetaldehyde. So your two products are going to be acetaldehyde and 1-iota-butane in this case. So vinylic and aromatic alcohols do not cleave. The other side does, I should say, vinylic and aromatic ethers don't cleave at the vinylic or aromatic residue. The other one will, assuming, well, unless you've got something like diphenyl ether, which that's a whole other question. So I guess if you added HBr to that, nothing would happen. There's a big bottle of this in the Singleton chemical stockroom. Sometimes people use this in that group. And I'm thinking, I have no idea how they even make that. How are we going to make that? You can't do it by an SN2 reaction, not an aromatic halide. So I don't know. I wonder how they make that. I do not know. Good. Well, I'm running out of time here. So let me show you what the exercise would have been, and it's thinking about that mechanism. So let's say that we had 2, 3, 4, this ether, and we treated it, or was that a 5-membered ring? Doesn't really matter. And let's say that we treated it with an excess of HCl, and our organic products will be that chloride and 1-chlorobutane. See if you can come up with a reasonable mechanism. And by the way, I can think of at least 2 mechanisms that are correct, depending on whether you want to cleave, depending on which of the carbon-oxygen bonds you want to cleave first. And I'll even get you started. Your first step is going to be protonation of the ether with HCl. And I'll just say another hint before I start working kind of behind you guys. You've got a choice now as to which of those 2 carbon-oxygen bonds you cleave first. And it doesn't matter. Either one of them is fine as long as you show it correctly. And that's where you're going to need to make a decision whether you use an SN1 reaction or an SN2 reaction. However, I'm sure that both of those actually happen. If you did this in real life, in some molecules, you'd cleave this one first, and in some, you'd cleave that one first. So they're both correct. I believe on the answer key or the answers that you'll get on eCampus once I fixed everything, I show the process where we cleave off the butyl group first. But let's consider what it would look like if we went the other way, because you certainly can. Well, this is a tertiary substrate, so this will go by an SN1 process. And so from this, we'll get our tertiary carbocation and 1-butanol. Looking like this. There's a question in chat about an extension on the homework. It's been extended. It should be due now on December 4th. I'll double check that when I get back to my office, but it's not due tonight. It's due December 4th. I just did, the reason I originally put it on tonight is I just didn't want to do the day after Thanksgiving, but I thought I pushed it back to December 4th. I'll go double check that. Oh, I did? Good. Well, okay, thanks. Yeah, everything, yeah, so we're all good. Okay, so we get our tertiary carbocation, and then all we need is chloride ion to attack the carbocation. That's where we get the 1-chloro-1-methyl cyclohexane from. And of course, we now need to get the other one to cleave. We're going to have to protonate that oxygen first, because we're in acidic medium. If you look at what we're given, this is definitely acidic. There's no way we're going to lose OH minus as a leaving group in a medium that's so acidic. So we do need to protonate that oxygen first. We'll get something that looks like this, the conjugate acid, and then this is going to go by an SN2 reaction since it's primary. And that will go straight to the 1-chlorobutane. So this is one way to do it. You'll see another way in the other answer key. However you spread this out, or whatever you write where, as long as you include everything, it's fine. For the homework, if you get more than an 80 average, you don't get extra credit. That is correct. But you need to get at least an 80% overall average to get full credit. Anything below that will be scaled upwards accordingly. Good, and I am out of time. So I guess I will see you all on Monday for our last class.